Okay, physics friends, here we are today with another problem for you. This one is another conservation of momentum problem, and it's an example of what we call maybe an explosion. So here's my situation. This is me. I'm in a canoe without a paddle, and I have a kitten with me. And the water is kind of choppy, and I need to get the kitten back on the dock, which is over here, because I don't want the kitten to swim in the choppy waters. So what am I going to do? I'm going to use the conservation of momentum, and I'm going to throw the kitten from the boat over to the dock. Okay? So let's see what's going to happen here. So let's say that the kitten, the boat, and we all have an initial velocity of 0 meters per second. We're at rest, and that's why the kitten, I can't get back to the dock. I don't have a paddle, and the kitten doesn't want to be wet, so we're sitting here at rest. We're kind of stuck. Okay, the kitten's mass of the kitten, let's say, is 3 kilograms, and then the mass of the boat plus me, or person, let's say, is 100 kilograms. Okay. And I'm going to chuck the kitten from the boat to the dock with a speed of 20 meters per second. That's pretty fast. That's fun. Okay. So let's look at the conservation of momentum here. Okay. So at the initial conditions, the boat, me, and the kitten were all at rest. So our m, which would be the momentum, the mass initial plus the initial velocity, right? And that's going to equal 2 separate momentums, right? So it's going to be, because we start as one object and we become more than one object. So the second half is the kitten is an object. So that's the mass of the kitten, and the final velocity of the kitten, that's kitten's momentum, plus the momentum of me and the boat. So that would be the mass of the boat and me times our final velocity. Okay? So this is the total initial momentum, which is all of us together. And then because we become separate objects, we have 2 separate final momentums. But their sum needs to equal the initial. Okay? And based on what I have here, if we're all at rest in a boat, the total initial momentum of this system is 0. Okay? But it still has to equal this on the other side. The mass of the kitten times its final velocity, plus the mass of me in the boat, plus my final velocity. Okay? So I'm going to move one of these terms to the other side because I can set them equal to each other. So I'm going to take the mass of the boat and me and our final velocity, and I'm going to set that equal to the mass of the kitten and the kitten's final velocity. Okay? So I have here some information. I know that the mass of the boat and me is 100 kilograms, and I need to know how fast I'm going to be going after I throw the kitten. And then the mass of the kitten here is 3 kilograms, and its final velocity after I throw is 20 meters per second. So this ends up being 100 V final, which is what I want, equals 3 times 20, which is 60. Okay. Oh, I'm sorry, I forgot. There should be a minus sign over here, because I subtracted that to the other side. Okay. And so then I'm going to divide by negative 100. So I get V final is equal to negative, what is that? 0.6? Yeah, 0.6 meters per second. That's the final velocity of me in the boat. Now what does that negative mean? It's telling you the direction. Right? So if I move the kitten in this direction, which I'm claiming is to be the positive direction, then the boat is going to be moving in the opposite direction, or it's going to be moving away from the dock. Okay. Normally when you have some sort of explosion type situation, that is the case. One object moves off in the positive direction and the other half moves in the other direction. So hopefully that helps you set up an explosion equation. Give it a try.